this talk is based off of a tutorial we have given at SIGMOD 2020. And the work that some of the work that I'm going to be presenting is joint work with my wonderful collaborators from IBM. So with that, let's get started. So what is the problem? The natural language querying has been sort of one of the holy grails, right? The idea of talking to a computer and then the computer interacting in natural language has always been very appealing. The problem in case of databases is the data is usually organized in very complex schemas, has very non-friendly names. People do not call them the business names. They kind of have a shorthand account and becomes ACC, so to speak. And the data and the relationships, most of the time, the data in a relational database is normalized, scattered in multiple tables, and the information you need is sort of in multiple places. So that basically creates some the level of complexity in the language. But the promise of the natural language interface is democratizing access to this data, because without such a simple interface, the mechanisms to access data is using high-level languages, query languages like SQL or Sparkle type of languages, and only people who know how to write those, how to program in those languages are able to access the data. So, and business, in an enterprise, especially business users are not savvy SQL users. They know how to interact with their dashboards. They kind of know how to read reports and look at charts, but they are not good at writing those queries. So enabling natural language queries basically democratizes exams and gives them the opportunity to interact with data. And finally, I also want to point out, and I'll try to spend some time here on the conversational aspects of this, because it is almost like having a conversation with your data. It's not always a single question, but a session of exploration. So a conversational interfaces are in that regard getting more popular. So let's basically start with the high-level challenges and what are the sort of the opportunities, why we think this is possible. The understanding user intent is the most difficult problem, because natural language is inherently ambiguous. When somebody asks for a question, there are other elements in natural language like the notation and other emphasis that basically turn the question into the same sentence into 5 different questions. And so understanding the user intent basically requires heavy natural language processing and the natural language understanding. So that's one the biggest challenge. And once you understand the intent, turning that intent into the target language, generating a query that is executable is the second big challenge. And as I just explained, how the data is complex, how the languages are difficult. So the good news is that for the first challenge and the natural language understanding and the natural language processing, there has been a lot of good progress in the research community over the last couple of years. GLAW and FastTax was sort of the first ones, but BERT seems to be emerging as the most popular language models. These are the deep learning models that kind of create feature vectors of the input sentences, and they are able to help with the entity tagging and semantic tagging and various other tasks, because they are able to provide more semantics, understand the similarities between text, and help disambiguate. And the other aspect is, as I said, people are very much interested in a dialogue with the data, and conversational agents have been also gaining popularity. Pretty much all of the major vendors, from IBM to Microsoft and Amazon and Google, everybody kind of have this assistance for you to build chatbots. And that basically becomes handy to build these interfaces. So how does this work? So at the very high level abstraction, there are really three big tasks that needs to happen for a natural language statement to be turned into a SQL or executable Sparkle query. The first step is semantic tagging, semantic parsing, semantic tagging, entity tagging, those different names. But it involves named entity extraction. It has a bunch of different names, but the net of it is when you, and this is where the heavy natural language processing goes into. The goal of the step is parsing the input statement from the user and understanding what are the entities, what are the elements, if you will, involved in the user query, in the user's input query. So this part is very important. And for the second step for interpretation, that basically includes relationship, identifying how these different entities in the input are related and how do they correspond to the database elements, to columns, tables. Do they require aggregation? Are are they used in filters? Are they expected to be returned? So understanding that semantics and interpreting the entities is this second step, and that's also non-trivial. Once you understand the meaning of the query and how it relates to the database elements, the last step is the SQL generation. And this is where heavy SQL knowledge or the I'm going to heavily talk about SQL. Some of these techniques apply to Sparkle type of structured queries as well. But the net of it is a query language. You can technically apply this to other, and in our prior work, we have generated the DSL on Elastic as well. But the structured query generation, the last step, basically builds off of the interpretation. So in general, there are really two approaches to the end-to-end natural language querying. One is the rule-based systems, and these are some of the early systems I'm going to show in a minute. And what they do is they basically clearly delineate all of these three steps, and they basically use rules or grammars for each step. They and the other end of the spectrum is the text-to-SQL systems, and these are more single holistic approaches. And I'm basically using this in a little bit of a abuse of the term because it is not one model that does the whole thing per se. They also have an ensemble of models doing multiple things, but there are it's really the models, different types of machine learning and deep learning models that basically do the whole end-to-end interpretation and query generation. So those are the two different approaches, and there are also in between approaches where, or more in between approaches are sort of emerging, where you might be using language models like BERT or other advanced techniques like Tapas to do the initial tagging phase, and then use, for example, grammar-based template slot filling type of approaches for the SQL generation. So all of these sort of different combinations are possible. And today, before I go into different systems, I want to give a timeline. I mean, as you see, there has been work in this space as early as early 90s. And I know you could challenge me to find papers even before that. So this definitely has been an area of interest for researchers for quite a while now. But what we have seen is around the 2000s, we have seen a lot of rule-based systems approach trying the natural language. As you can see, after 2016, there has been a flurry of text-to-SQL systems thanks to the advancements in the deep learning technologies and the language models based off of the deep learning models like BERT. So as you can see, the trend right now is the big shift to text-to-SQL systems. Okay, so what are we going to cover today? So I'm going to talk about, first I'm going to talk about some of the complexity of the queries. How did things evolve? What are the challenges involved in each of these different cases? Single table queries, queries with joins, and the more complex queries with subqueries with increasing complexity. And the other set of things, depending on time, I'm going to talk about rule-based and text, give you the high-level characteristics of the systems, and also talk about some sample examples. I would say I'm not going to cover all those systems. It is a very active field. There has been a lot of tutorials and surveys on natural languages lately, and more and more systems come out every day. What my goal here is just to give you the general characteristics of different approaches and sample systems and how they do it. And then I also want to talk a little bit about, maybe depending on time, spend time on how to extend to dialogue. As I said, this interaction with data is important. So if we look back, we basically see two sort of communities interested in this problem. In the IR search communities, basically, the problem they are trying to address has evolved naturally from keyword search, right? In the keyword search, you type in a bunch of keywords. The natural evolution is writing a statement. And if you look, and if you think about the early days of search on the internet, you could just type keyword search. Today in Google, when you go to Google search, you can type in a question, who is the CEO of Google, and you get answers, info boxes, and so on and so forth. So with that, there has been a natural evolution from search to query answering, but the queries that basically the queries that target or they address are usually lookup queries, information lookup. Who and what is the capital of Germany? Or who is the CEO of Google? On the other hand of the spectrum, the database community is interested in this one, and the database community likes its SQL and analytics and the complex queries. So they, the kind of queries they want to do with this is really very complex analysis queries. And an example is what is the average income per state in Germany. So this type of interactions are kind of getting popularity. Actually, let me go back. One of the other things that is happening is BI tools like IBM Cognos or Amazon Quick Insights, Power BI, Tableau. They are all starting to introduce some natural language interfaces into their products. And Gartner actually predicts that the dashboards will be replaced by natural language and interactive interfaces going forward, because it, as I said at the beginning, it democratizes access to business users. And at the end of the day, data is for analytics, understanding your business insights. So as things move to more enterprise-focused areas, BI-type complex queries are becoming more and more important and the target of natural language interfaces. So, and of course, depending on the query type or the application, there are different challenges to be addressed, and naturally different techniques work better on one or the other on different systems. Natural language interface to databases, that's the NLIDB acronym. I am not sure if I spelled it out anywhere, sorry about that. Okay, so let's talk about increasing query complexity. So you could basically think of queries as simple as single table queries that only do lookups. Show me this SSM for John Smith. Or you can also think about complex queries on a single table. You don't need to sort of have very simple queries because the query is on a single table. You can have very, very complex queries on a single table. And in some extent, as I said, most of the data is normalized into multiple tables. If you think about a star schema type of OLAP schema, and you denormalize, you can think of it as a single table, fact table joined with all the dimensions, and you can express very complex queries on such a table. What is the average amount of loans approved by year? So all of those, and if you look at these queries, there is aggregation, there is grouping, there is probably additional filters. So you can go down the complexity quite a bit. And on the other hand, you can also express simple queries that are across multiple tables. Which company did the CEO of Google work for? You have a table with CEOs and their work history, another table with the companies and their CEOs, and you need a join. Although the query looks like a simple lookup query. And then at the end of the spectrum are very complex analytical queries, which I will go into. So what are the challenges in all of this? The first task always is entity identification. What are the entities mentioned in the query? Like the first one, the SSN and John Smith. Identifying those are the first important tasks for natural language querying. And the second, and then domain understanding. If I ask, show me top loans, what does top mean over there? Do I mean the largest amounts, or do I mean the shortest duration? How does top manifest itself in different domain? What are the best doctors? So how do you basically determine those type of things? And also, what are the columns? What are measures and dimensions? When you have an amount column, that's a measure that probably your aggregation is meant for that column. And the dimensions are probably meant for more filtering columns. So understanding the domain and understanding the relationships between these entities in the domain are important challenges. And the last thing is, of course, how do you basically correlate that to the database tables and columns? And again, the last step is always how do they come together in a query. So I'm going to skip, in the interest of time, the aggregations. So the analytical queries could basically contain a lot of complexity. It could basically have comparisons, and the comparisons could be simple comparisons. And in analysis, you distinguish between time, because time is an important dimension in all of analytics, and most of the systems actually have special annotators understanding time. And then the aggregations. So if is the predicate on simple columns or aggregation results? Show me people with loans more than 50,000. You need to aggregate the loans before you apply the predicate. And this is almost like a group by having clause. So is your predicate in the where clause, or is it in the having clause? So you need to understand the differences. And then top K queries, comparisons, window aggregations, and all that. So these are basically just some elements of analytical queries, and there are not a lot of systems out there today that can handle all of this complexity. There are prototypes, but not many that can handle all of it. So, okay, okay, I should have removed the animations. Okay, challenges. In analytical queries, the measures are not always correspond to columns that are stored in the tables. Sometimes you need to basically have complex computations to figure out, to compute what the user is asking. So that basically becomes non-trivial, because it's almost you are interpreting a mathematical formula from a language description. And also, there are implicit arguments that require domain reasoning. And what we have seen is solving these challenges requires both a rich understanding of the linguistic constructs as well as domain. So it needs to be, there is some level of deep domain understanding needs to be sort of incorporated with the rich NLP, NLU techniques. Okay, so that's basically just a general description of the complexities and different tasks involved. Let's start looking into how people have approached this, right? So as I said, the first approach I'm going to talk about is the rule-based approaches. So what distinguishes them is they recognize entities and relationships. So show me Amazon customers who are also who are from Seattle. So the thing is, Amazon is the company, right? And Seattle is the city, and then the customers are sort of the person. Understanding the different entities and how they relate to each other is key, actually that's key for all approaches. It's just that in the rule-based approaches, to understand, identify these entities, usually they exploit a semantic index, some sort of inverted index, and with different levels of complexity, they could use taxonomy of terms or synonyms, like WordNet or some other proprietary ones. And the most complex one is they can also use ontologies. So, and combination of these things. So the major characteristics of rule-based systems is they rely on this index structures, taxonomies, and ontologies to help do the entity tagging in the user statement. So the index structures and taxonomies, the common approaches is parsing the language query into some mission readable or semantic intermediate format. And when you do that, you could be, if you go to the query, show me Amazon customers, right? Show me is the intent that you want to query result. You can drop those keywords. So you basically identify things that needs to be satisfied in the query, and it's almost like identifying the slots that needs to be filled in. So and then what you do is you actually say, okay, Amazon is one of those, and you look up in an index to determine that Amazon actually is an instance of a company name. So these three intermediate format, identifying the slots and filling in the slots using an inverted index is another characteristics. So I'm listing a bunch of references here that are samples, that are examples of this approach. And but I'm not going to go and I'm going to talk about some of them. I'm not going to cover everything. So the first one I wanted to talk about was one of the earliest ones, going all the way to 2006, 2008. So this one basically parses the query into DNFs and basically tries to match each, like identify the uses an inverted index to identify the entities, and then creates possible interpretations, multiple interpretations. So if you just type in Clint Eastwood and thriller, it could be thrillers directed by Clint Eastwood, thrillers in which Clint Eastwood is acting, thrillers directed by Clint Eastwood, in which he's also acting. So there are multiple interpretations that you can, by just keywords, you can identify. So what this paper does is they basically create the interpretations, and then they basically use some sort of ranked mechanism to choose the final interpretation. The next one I'm going to mention is another one that also uses the inverted index and uses these intermediate representations and the semantic index for figuring out which interpretation is correct. Okay, so let's another one that basically has gotten a lot of popularity and created interest in our community was the Nalir paper, which won the Best Paper Award in VLDB 14. And this one in particular Again, what it does is it uses the, let me go back for a second. So Precise just uses the inverted index, makes use of a taxonomy from WordNet to help the identifications. And Nalir also used WordNet terms and synonyms to help disambiguate. So it basically uses parses the input using the Stanford NLP core library, and then uses WordNet to kind of do disambiguation. And it provides, it basically asks the user to disambiguate. So if there are multiple interpretations of the same query, or same term, it really asks the user to kind of help. And this could be a good approach, including the user in the disambiguation process. But if you have a lot of disambiguity and if you end up asking too many questions, then it also becomes cumbersome and not very user-friendly. And I mean, it basically creates this parse tree, which in turn it turns into a SQL query. Again, this is an example of a rule-based approach because it basically has slots and knows how to convert those slots or templates into a SQL query. So the most, I guess, semantically rich thing, external auxiliary structure people have used is the ontology. So once you identify your entities in the input statement, you look into those entity slots in an ontology, and the ontology basically not only gives you the individual concepts, but basically tells you how they are connected, and helps you identify the possible join paths. Of course, understanding how the ontology and the database correspond to each other and how they are related is another important aspect of using an ontology. So there are a bunch of works that use the ontology, and I'm just listing a bunch of them here. And I'm going to talk about a few of those. I chose Bella because this is an example. This is actually an example where the output is a Sparkle query. This one doesn't produce SQL. This one actually produces Sparkle. And what is the currency of the Czech Republic? As you see, it has the templates. It's really a templated query. It does use an inverted index lookup they built from DPpedia, and when they look up the Czech Republic, they basically find the link to DPpedia and the currency as well, and they basically also use some sort of a similarity. If they cannot find an exact match, they find the closest property that is to the entity they found, and then by using this lookup results, they start filling in the slots and creating interpretations. So this is a very, I guess, common approach, and this is one of the early works on this one that produces Sparkle queries. Okay, so this one is a little about the same year, I think, another work that uses the ontologies. This one looks up the keywords in both the data. If there's an inverted index, they look that indexes the instance values in the database. And again, most of the time people do not, if you look into your database, you have columns of time numbers and then text, right? The time, as I said, is a spatial dimension in most of the natural language. You have spatial annotators to understand time. You don't really index time columns. And the numbers, again, you don't index number columns. What you really index in the semantic index and are number distinct values in the textual fields. And this could also be interesting because short text, like the names of cities, addresses, but you are not really indexing long description fields and others, depending on the system that basically uses different information. And again, it uses that index, and then also queries the ontology, and they call it the metadata warehouse, and they take the synonyms into account, and they again use DPpedia for that information. And they the thing is, most often a single term or single entity from the query will correspond to multiple multiple entities in these indexes, and or have synonyms, and that will end up with multiple interpretations. And if you think about having a number of tokens, and then each token have multiple interpretations and multiple ways of connecting, so you can see that there are you can end up with a lot of different interpretations. And they used ontology and relationships to help disambiguate with these interpretations. And I'm going, in the interest of time, I'm going to skip this one and go directly to our approach, which is Athena. Again, this was a joint work we did with our colleagues in India Research Lab. And Athena basically it created this notion of a two-step interpretation, where the first step basically, Athena also uses an ontology, and Athena knows the mapping from the ontology to the database elements, and then it uses that mapping to provide physical logical independence, in the sense that the query interpretation doesn't have to refer to the database, it refers to the ontology concepts and relationships. And for that, Athena provides an intermediate language called the ontology query language, and that's phase one. And then from the ontology query language, you can go to a structured query generation from translation. So what this approach brought us in Athena project is we were able to, for example, for JSON, querying JSON documents, we were able to use Elasticsearch JSON DSL, or store it in a relational database and use the JSON language of the database to query the JSON fields. But the net of it is the domain ontology abstracts out the physical storage and the underlying schema, as well as the query language to kind of query it. That was sort of the target. And Athena also follows the similar steps that I have basically already talked about. It basically parses. It has some special tokens, like the last 5 years is identified as a time frame using the time annotator, and things like how many are used as linguistic clues to basically imply count aggregation. And the individual, like IBM, stocks, people are extracted as potential entities matching into ontology elements. And then what the Athena does is basically creates candidates for each of these tokens, and then creates interpretations combining all the tokens in possible different ways, which we call the interpretation tree, and basically uses a Steiner tree approach based most spanning tree, finds the most complex spanning tree to pick up the most likely interpretation. So initial Athena paper basically supported a lot of the query functionality, but didn't address complex analytical queries, especially nested queries. So Athena++ basically was the work that we did to extend it to such complexity. And in the interest of time, I'm going to skip this one. But the high level thing is what Athena++ does when it parses the statement. It basically looks for linguistic clues to identify that there is nesting involved in the query. This is a nested query, and then basically creates inner outer, sort of creates sets of tokens for inner outer query blocks, and then creates interpretations for inner outer, and also identifies how they should be connected. What is the join condition for the inner and outer? For that one, it uses a combination of linguistic clues as well as information from the ontology and the deep domain understanding that comes with it. So to summarize, what are the pros and cons of the rule-based, entity-based approaches? It basically allows handling input queries because the templated approach allows you to create as complex templates as you could basically handle, and easier to incorporate the domain knowledge, especially through the use of taxonomies and ontologies, and doesn't require training because there's no supervised learning involved in these rule-based approaches. But what also happens is it's very sensitive to variations in the user query. So paraphrases of the same query, it's not robust against those. And it basically, I guess the natural language understanding part of it is not as robust as some of the techniques like language models, like BERT. So that's sort of the biggest drawback of this approach. Okay, so let's talk about the next group, the text-to SQL approaches. We call this text-to-SQL approaches where people basically use, the general idea is using supervised machine learning, deep learning techniques, usually RNNs, recurrent neural networks, on a set of question-answer pairs. And this requires training data, obviously, and the input is the natural language query, the output is the SQL statement that gets generated. Most of them focus on a good model based off of WikiSQL, and I'll talk about that in a minute. The follow-up works extend this, support more complex queries. The WikiSQL one, the sec2SQL was actually generating the queries on single tables. Some basically support more complex queries. But it basically, they try to adapt. In addition, the community also look into the challenge of generating training data. Is the main drawback of all of these approaches. It requires a lot of training data. And if you think about the richness of the SQL query, I'm not talking about Sparkle, but the SQL query, the kind of queries you can express, and the fact that the same information could be expressed using different SQL syntax, it basically tells you how complex the training, sample generation, or how many training examples it requires to kind of learn all of those variations. So with that, the community also looked how to automate the training data generation, especially coming from the database community. A lot of the text-to-SQL approaches actually come from the search NLP communities. So that's another highlight. So again, and if you look into the progression, this sequence-to-sequence models, sequence-to-sequence models basically formulate the problem as a machine translation problem, with the input be the user query and SQL being the source and the target of the translation, using RNNs. And there has been a lot of variation based off of that idea. Sec2SQL paper being sort of the seminal one that kind of started that line of work, but followed by a bunch of others. And then the challenge that has been identified in all of those is the domain adaptation. So how do you basically tackle the domain adaptation problem? And of course, the training data is the other approach. So let's start with sequence to SQL. As I said, this is sort of a seminal paper that started a lot of the early work on this one. It's one of the early work from Salesforce, adapting the deep neural network machine-to-machine translation. The inputs to the sec2SQL are questions and the columns of the table. It generates the corresponding SQL query, which is again executed against the database using after the training. And this paper also provided a large corpus of labeled data on Wikipedia base, and that was also the reason why it sort of created a lot of follow-up research, because there was labeled data available to improve upon. So it basically employs the because it is using mission-to-mission translation, the output SQL query could not be syntactically correct always, and it basically has a reward mechanism to kind of fix the errors that was produced in the output. So okay, so I think we started late. Is it okay if I go over 5 minutes into beyond the hour?
Yeah, I think that it is no problem. In fact, as we started, we had a delay, or I think that of 10 minutes, you can take 5 or 10 minutes more. No,
okay.
I think that's no problem.
Okay.
Yeah.
Okay, good. Because so the seek to SQL basically produces SQL on single tables, but captures aggregation, selection. I mean, it basically identifies the aggregation operation. It also then understands the selection and the where clause. So it kind of basically tries to almost slot filling type of thing. And for aggregation operation, it uses a multi-layer perception over hidden representations, and obtains a distribution over the possible of aggregations. And they really look into 4 different aggregations: count, min, max, or nothing. And then for the selection columns, these are the return columns. First encodes each column name with using an LSTM and another deep learning architecture, and uses the last encoder state as the column's representation. And it then uses this multi-layer network to compute a score for each of the column. And the last one, it uses the reinforcement learning to learn a policy directly optimizing the expected correctness of the execution. As I said, this step is added to kind of make sure the output produced is an executable statement. So there are a bunch of things that are interesting, that was interesting in this paper, because this is a sequence-based approach. The order of predicates in the where clause was sort of matter, and they basically have done work so that they made it the order non-significant. And they basically showed results on Wikipedia data and the WikiSQL. They, as I said, they labeled a lot of the data and made that data set and the queries available, which basically triggered a lot of the follow-up work. So with that, I kind of want to move on. So the other one that I want to talk about is the SQLnet. This one basically uses sketch-based approach to remove the reinforcement learning part of the sec to SQL. These are all variations or follow-up work on the sec to SQL. Specifically, the sketch is designed to align with the SQL grammar. So it kind of almost like the sketch, what they call sketches, is really like a templates, and they basically capture the dependency of the predictions. The prediction of so in the sketch there are multiple slots, and each prediction basically tries to fill in one slot. So, and they use column attention networks to basically fill in the. Okay, so the SQL sketch would look like something like this, and the natural language will basically fill in the. And they are, as I said, they are using multiple models and complex architectures. In this case, they are using 2 LSTM, one for the question and for the column name. The early approaches used in all of this, what they do is they first take the natural language query and create a vector representation, some sort of an embedding out of that. That basically becomes the input to the deep learning architectures. In the beginning, they were basically creating one feature vector for both the question and the answer, but earlier the subsequent works basically separated the question and the database elements when they're creating this feature vectors. Okay, TypeSQL is another sketch-based approach, but they also utilize types extracted from a knowledge graph to basically improve the semantic understanding of the individual entities. And they also use a bidirectional LSTM to encode the words in the question. Okay, I kind of want to go a little faster. And TypeSQL assigns numbers and dates in the question so that basically understands different data types because the identify named entities is searches for 5 types of entities from freebase. That's basically where the knowledge graph that they have been using to kind of bring in more semantic information. And they have 5 types: person, place, country, organization, and sport. So they really, that the type SQL basically comes from there, right? They are really searching for typed entities from a knowledge graph to fill in the slots for the predictions. Okay, I think I'm gonna go a little faster now and skip some of these ones. Then one of the other challenges was the domain adaptation. In the earlier works was, if you think about the sequence sec2sql, it was basically formulating the problem just as a machine translation problem, is translating a sequence of tokens to another sequence of tokens. But domain adaptation has become a challenge, and understanding the domain semantics has become a sense. And they basically started using more the subsequent approaches, started to basically build techniques to address these challenges. So one of them was the adversarial methods for the domain adaptation. And the key idea is separating out the data-specific components. And they also try to, for example, what is the height? So that's basically the intuition was this domain specific knowledge is not a strong signal. If they basically train the model heavily on a particular domain, moving to a different domain becomes a challenge. So that's why they are really trying to remove the domain specific aspects to learn the structured or the more templates and sketches beyond just the individual domains. Okay, so I'll skip this. Tapas is one that is from Google, so I want to spend a little bit of time on Tapas. This was sort of interesting because Tapas evolved from BERT, and it addresses the cross-domain adaptation challenge from a different angle and setting. Instead of applying semantic parsing and translating a natural language question to a SQL to provide answers, the task here is to answer a natural language query by selecting cells in a given table. So in that regard, the key idea of Tapas is basically extending BERT's architecture to encode the question with tabular data structure so that they take the cell structure of the tables into account, and this pre-trained model can point directly to the answer. So that was sort of the Tapas approach to the system first embed the question to a BERT input, right? They are using BERT language models, and also the table is also embedded as natural language, the whole table. So as you can see, the Tapas is not really scalable to large number of tables or really wide tables because they are really encoding individual cells of the table, and the prediction is really the answer to the questions. So, but that basically created more work. Okay, I'm gonna skip. So the RAT-SQL is a very recent work, and this might be the last one I wanted to, I'll talk about. It addresses the challenge in the encoding. As I said, the way you encode the data, the individual columns, into the training basically is key here. And the alignment, so the challenge in encoding the database relation and modeling alignment between the database columns and their mentions in the NL query is the challenge that SQL is trying to address. The goal is still to generalize the semantic parsing models without domain specification for domain adaptation. And the key idea is to use relational aware self-attention in the encoder to address the schema encoding, linking, and feature representation. Then it combines this global, actually, let me finish up the, okay. And so they basically have a schema layer, that layer, and a tree encoder, and they basically combine this over predefined relations. In the interest of time, I'm not going to go further detail because there's one other line of work, which is the idea of generating training samples for all of this. And the people from the database community basically addressed that issue. And what it was, it provided is, you provide a bunch of, first of all, DPPAL works with any of this deep learning based or text to SQL systems. What the DPPAL addresses is generating the training data to train and use any of this text to SQL system. And they basically, you provide a bunch of templates, and then it basically creates you this training examples and trains the network, whatever system it is, to produce the result. So they basically have data augmentation and optimization, the details of which I will skip. Okay, so the takeaways, because these things are heavily, as I said, most of the time the input and the input basically, the user's input statement as well as the database schema elements are encoded as embeddings. Those embeddings and feature vectors are very robust to language variations, and they are also able to identify similar terms, if you will. And with that, they are very robust to variations, and they basically they have been producing very accurate results as well. They have high precision, but the problem is they do not necessarily because they need training samples. They do not handle a rich variety of SQL queries yet, and they don't really handle complex queries as much. But there are works that are kind of going after this problem as well. Okay. I want to basically mention one hybrid approach before moving into the last part of the talk. The DB tagger basically is sort of a hybrid. What it does is it actually uses deep learning architecture based on bidirectional graph recurrent units, the GRUs for entity tagging. So if you remember the tree in different parts, the semantic tagging, the interpretation, and the SQL generation, what they do is they basically use the deep learning methods for the entity tagging part, and they basically provide a bunch of different tagging, different learning. They do multitask learning by learning different types of tags, and they combine that. But they can be combined with any rule-based system. Like in their paper, they have implementations combining with Nalir, for example, because once they identify the entities and do the slot filling, the SQL generation can be grammar or rule-based. And that basically gives it kind of addresses the weaknesses of both, if you will. The part where the rule-based systems fail is the robustness. And if you do the semantic tagging using the language models and address that robustness problem, then the complexity problem can be addressed with the rule-based, grammar-based approach, and then the more complex queries can be generated. So that sort of is a trade-off, and I think this we will see more and more hybrid approaches. So I kind of want to spend a few minutes on dialogue. The natural next step is, of course, having a session of queries and data exploration session. And the advantages, one is basically between multiple turns, there is context. And you basically, this persistent context can be used between iterations for disambiguation. If I'm talking about admissions to the hospital, I know that's sort of the context if I ask another question after that, even if it is underspecified. If I ask, show me the cost incurred claims by female population over the age of 55 in North America. What about males? So if only say males, but I understand the whole context because it is a dialogue. And you also have a more natural way of disambiguating. Did you mean the male population or the female or both? Type of did you mean type of clarification is more natural in a dialogue. So in a conversation system, a lot of them have different architectures, but there are a couple of common elements, and they are intent, entities, and the dialogue. So intent is the user intent. What is the intent of this particular statement? And entities are the entities included in that. And dialogue basically figures out the structure. If the user says this, you may want to interpret this way or this way, and then you can basically build a conversation using dialogue structure. And then, of course, it connects to a data source to execute the query and get the results. I want to cover a few of the slides and skip most of it. So in the intent specification, this is again, identifying intent is one of the hardest challenges. And there has been different approaches for intent classification, similar to the NLQ, the natural language query. So there are ML classifiers. These are just every intent is like a class, and you are using a classifier to identify which intent the user meant. Then there are other deep learning techniques similar to SEQ-to-SQL. They are exploiting the sequence-to-sequence networks. And there are ones that utilize more user feedback because that can come naturally in a dialogue. And there are also others who utilize the conversational context to basically disambiguate further. And these are systems that I will not have time to go into further detail. And I'm going to skip the ML classifier. As I said, you kind of treat the problem as a multi-class classification problem and use known techniques for random forest or any other technique that you. So I want to basically, skip to entity specification. This is the other important component in conversation entities. And they basically, if you think about it, entities are really the domain vocabularies. And they can refer to metadata or the data. And then the more synonyms and taxonomies and the complex reasoning you provide on these entities, the more sophisticated or the higher your recall, because you can understand more. And what happens is in a lot of the systems, it's slot filling where you have multiple entities, and then you can use indexes, or you can use machine learning type of techniques to basically identify the entities in the user utterance. So, there are a bunch of challenges. Of course, the state can be large, especially if you accumulate state by keeping context from prior runs, when to reset is important. And the deep domain understanding, domain specific synonyms, when kidney failure, renal failure, the more colloquial terms versus the medical terms, understanding all of that is very specific to the domain. And of course, there's also further complexity by taxonomies and the hierarchies. Like SNOMED provides a very rich hierarchy of disease codes and relationships. And understanding that hierarchy allows further increase in recall. And the dialogue, again, is basically another challenge, how to basically structure the dialogue so that it feels more natural conversation, as well as leads to disambiguation. So I'm gonna skip that. And the training examples is where, again, these are all models that you need to train. It's mostly supervised learning techniques. The thing is, because a lot of them are slots or template based, there's a lot of room for automation for generating the training examples. But you kind of need to figure out how to incorporate the domain specific knowledge. It's that domain specialization that basically, or domain adaptation, that becomes a challenge. Okay, so we did some work in this space where we kind of use an ontology to bootstrap a conversation service, because from an ontology we can extract entities, and then by identifying paths in the ontology, we can identify query patterns and represent each of them as intents, and also speed up the training sample generation using that. So this one was a system we built on top of a medical knowledge base. So the ontology here represents that. So we also did some work on conversational BI, similar to, we basically wanted to use the same approach. It was challenging to figure out the ontology. What does the ontology represent? Because we know once we have the ontology, how to kind of populate or automate the generation of intense entities and training samples. We ended up basically creating an ontology off of the business model, or the cube definition, which includes the information about to take advantage of the fact that in a BI domain, there are a fixed set of patterns people would like to do. And we use those patterns to basically bootstrap the intents. Again, once you have those patterns, you can basically write code to automate the generation of patterns. So with that, I'm going to skip this in the interest of time, and basically mention that another important, a very important piece to the puzzle is the benchmarks, because benchmarks allows you to track progress, and it's also a common, basically, if you will, if everybody uses the same data set and basically reports the accuracy numbers or the complexity increase and adds more queries to the benchmarks, it basically allows the community to evolve and track progress. And actually, I was planning to do that, but I didn't. If you go to any of this web, there are a ton of these emerging ones. From the early ones, WikiSQL is very, very popular. Also, Wikitable came up recently. Spider basically tries to address the domain adaptation by providing a lot of different domain tables from very, very different domains in the query set, so that to test the domain robustness of the system. Firebase is targeted really for BI workloads and analytic queries, and all of those. If you go to their web pages, what you will see is there's like a leaderboard. You'll see the latest results, the accuracy numbers, the precision numbers, and the systems and the references to it. So this is a very exciting time for natural language to data research, and there's a lot going on. So with that, I'll directly talk about a few of the open challenges. The complex, we still haven't made really a lot of progress on complex queries, on complex databases. A lot of these systems still work on simpler schemas, and if you'll go into those benchmarks, you'll see that WikiSQL is on single tables, Spider is on single tables, so there is not a lot of complexity, but to be adapted in the enterprise, you need to be able to handle those. And hybrid approaches, I already said, have the promise of combining the strengths of different approaches and producing better results. And we are now starting to see more systems using this approach. Language models are pretty much established as the best semantic tagging entity identification mechanism, but incorporating taxonomies and ontologies brings a lot of semantic information. So there is basically work to figure out how to do both in a meaningful way. And the other big challenge in all of the systems is trust and explainability, especially if you are basically asking what is the average loan in the last quarter, or the questions that come back with charts or aggregated numbers. Trusting those numbers that the query really did what you asked is important, and that goes back to explainability, explaining how you came, what you interpreted, and how you interpreted. And we already talked about conversation and benchmarks. So okay, I think I'm going to conclude. This is a very active area, and both from NLP and database communities, and we basically covered examples. We see that the language models and the natural language understanding advances in the last 5 years especially have been a major problem, and is now basically giving us the hope. But I have worked for enterprise companies, and I can tell you it is not a widely used technology in the enterprise yet. And having a conversation with your data for analytics is sort of the next wave. And Gartner also predicts that. With that, thank you.